Hey guys, so today should be pretty short and sweet. I just want to start out with going over protons, neutrons, and electrons again real quick, just to review over that with the isotopes and ions. Okay, so just a quick thing here. What happens when you change the number of protons? Okay, so the number of protons defines what atom you're talking about. So if you're changing the number of protons, you're changing what element you're talking about. So if you go from 8 protons to 9, you're going from talking about oxygen to fluorine, for example. Neutrons, if you change the number of neutrons, you're changing the mass of the atom, which also changes its stability. So you're going to create an isotope if you do that. So when you're changing the mass, the neutrons, that's the isotope. Electrons is the last one. So if we're changing the amount of electrons, you are changing the bounds of the charge. So that means that there might be more protons or there might be fewer protons, and that's going to create an ion. So we will talk a lot more about ions later on when we're doing bonding. But for now, just know the difference between an isotope and an ion. That's really important. And that if you change the protons, you're changing what you're talking about. So today we're going to be talking about molar mass, using Avogadro's number, and some more converting or dimensional analysis. So just a reminder, the atomic number is your number of protons. We know that isotopes are going to be atoms that are the same element but have a different mass. So if you have carbon and one has a mass of 14 and one has a mass of 12, they're both carbon, but they're just different isotopes of carbon. And then to find the mass number, it's protons plus neutrons. So if you're trying to figure out how many neutrons there are, it's always going to be the mass minus the protons. So with our relative atomic mass, this is used more for consistency than anything else. So when we start labeling these and we have values for atomic masses, we're going to label them as AMUs. So that's the atomic mass unit. It's just the standard unit that we're going to use to talk about atomic mass. So that really applies to your subatomic particles. That's where you'll see it most often. So if you're talking about protons, neutrons, or electrons, we say that generally speaking, protons and neutrons have mass and electrons don't. We know that electrons do have mass, but it's just very, very, very tiny. So those are atomic mass units. Okay, so that's what you would measure that in. They're not, a proton isn't like 1 gram, it's 1 atomic mass unit. So when you guys look at your periodic tables, and this I did, I forgot to post this yesterday and I'll add it today, but when you guys use your periodic tables, pretty much any periodic table is going to get the job done, but I would recommend ptable.com. It's just the letter P, the word table.com. It's a really good resource. So you can click on different atoms, you can hover over them, and you get all this information. So when you're looking at a periodic table and you see the mass number at the bottom, so if you're looking at oxygen, the mass is going to be 15.999 repeating, or 15.998. So when you look at that, that's the average of all of the naturally occurring isotopes of each element. Okay, because we know that you can't have a fraction of a subatomic particle. So you're not going to have an atom that has like 8.9 neutrons in it. That wouldn't happen. You would have 9 neutrons or you would have 8 neutrons. So the average atomic mass is the weighted average. So it's similar to how your grades are weighted. So well, actually, this is no longer accurate for the grades in your class. So assignments are 20%, labs are 20%, and then tests are 50%. So tests are 60% now. So your overall score is going to depend on your weighted average. It's no different than, I'm sure most of you are in AP classes and have taken many honors classes, so you know that you have like a weighted GPA. So some classes count for more than others. So if you look at this example on the side here, these are 2 isotopes of carbon. So this is carbon 12, the mass is 12, and this carbon 13, its mass is 13. So if we're looking at this, if you look on your periodic table, you'll see that it lists the atomic mass as 12.01. And that's because the naturally occurring isotopes, 99% of the naturally occurring atoms of carbon have a mass of 12. So 99% of them in the whole world have a mass of 12. But there's also this 1% that has a mass of 13. So to calculate the atomic weight average, you're going to have 12. So your isotope of 12 times the percent that it represents, plus the second isotope mass times the percent it represents. So you get these values and you add them together for your average atomic mass. So when we're calculating the mass of your average atomic masses, we need to know what isotopes exist and then the percent of abundance of each one. So in this example, we're looking at oxygen. Oxygen does have 3 naturally occurring isotopes. So we have oxygen 16, 17, and 18. The percent of those isotopes are listed there. So if you look at those, obviously oxygen 16 is the most common, and then oxygen 17 and 18 are fairly rare. So to calculate the average atomic mass, down here we have the mass of oxygen 16 times the percent. Remember that you wouldn't want to just multiply it by 99.7, right? We have to move our decimal point over to turn that into a number we can work with. So we've got the percent of the abundance times the mass of that particular isotope, plus the percent of the abundance of the next one times its isotope mass, plus the percent of the abundance and times the isotope mass. So when you get all of those, you get all these little numbers and you add them all up. Okay, and so then this is going to be your average atomic mass for oxygen. So this number, when you're calculating average atomic mass, should match what's on the periodic table. Or be very, very close to it. So if your very last number is off a little bit, that's okay. It's probably just a rounding issue. That's fine, because if you look at a bunch of different periodic tables, they're all going to have slightly different atomic masses anyway. So that's how you can double check yourself. So you calculate your average atomic mass. It should match what's on the periodic table. So that being said, it's important to show your work when you're doing these. You don't have to show every single step, but you would need to at least show this part, this top line here, just show how you set that up, and you're not just copying it down off the periodic table. So if you were going to try this, so these are 3 different isotopes of uranium. So we have uranium-234. It's a very rarely occurring isotope. 235, also pretty rare. 99.3% of all isotopes of uranium found on Earth are uranium-238. So we're going to multiply these, okay? So you're going to change this 0.005% into a decimal. So to do that, we're moving our decimal point 2 spots to the left. Multiply it by that mass, plus the next percentage times its mass, plus the next percentage times its mass, and then you add those results to get your average atomic mass of uranium is 238 AMU. So this, I obviously rounded it because I don't think that would have come out to exactly 238, but it does match what's on the periodic table, and it does match this if you're looking at it logically, right? So you know that if 99% of the naturally occurring isotopes have a mass of 238, your average atomic mass should be pretty much right on 238, right? Because there's a very, very small percentage of anything else naturally occurring. So the last thing we're going to talk about is relating that mass to atoms. I'm sure some of you have heard of Avogadro's number. You probably maybe have used it in physical science. But basically, it's just a quantity we use to describe atoms, since atoms are very, very tiny. So if we were counting individual atoms all of the time, you would have just enormous numbers to work with. So we use Avogadro's number. Sorry about that. I got distracted there by somebody in the storage room behind me. So we're going to use Avogadro's number to describe quantities of atoms. So you can relate that to the mole, which is a new unit we'll be talking about, and molar mass. So when we talk about a mole of something, this won't come up a lot as far as having to know this by its definition, but you do want to just understand kind of where this value comes from. So a mole is going to be the amount of a substance that contains as many particles as there are atoms in exactly 12 grams of carbon-12. So I know that seems like a very like strange thing to compare everything to, but it's just what they chose. So it's no different than someone along the line decided that a dozen meant 12. Okay, so if we are talking about a mole means the amount of atoms in exactly 12 grams of carbon-12. So if you look at this picture, this is representing 1 mole of each of these different substances. So you can see that that's not going to be the same in every single one. Like 1 mole of carbon is pretty similar to 1 mole of sulfur, but they're very obviously different from the other 3. So copper, mercury, and iron are not going to be looking the same as far as how much you're looking at. So if you see this, you say like, I need 2 mole of something, that's just a measurement. And I'll talk about right now how to figure out how much that is. So with Avogadro's number, so how many particles is in 1 mole, that's 6.02 times 10 to the 23rd. Okay, so if we go back, we're talking about 1 mole. We talked about it's exactly 12 grams of carbon-12. That number is Avogadro's number. So 1 mole of something is 6.02 times 10 to the 23rd. You do need to know this number. You'll want to be comfortable with that and remember it. So kind of with this comparison, this designation of the standard of a mole, that means that exactly 12 grams of carbon is equal to 6.02 times 10 to the 23rd carbon atoms. So you can also measure substances using molar mass. So the mass of 1 mole of a pure substance is called its molar mass. So if we're trying to figure out how many grams are in that mole, you would use molar mass. So molar mass is going to be written in units of grams per mole. And yes, mole is abbreviated as MOL because chemists will abbreviate anything they can. So even though mole is just 4 letters, we're going to abbreviate mole down to 3. This is going to be equal to the atomic mass. And then 1 molar mass of an element contains 1 mole of atoms. So if you have just a sample of 6.94 grams of lithium, if that's 1 mole of lithium, it's going to be equal to 6.94 grams per mole for its molar mass. So the molar mass is going to be equal to just the mass. So that'll be very similar in anything we work on. So here's a nice little triangle. I know some of you guys enjoy having triangles to figure out how to get your equations. So depending on what you're trying to convert to, this is how you know what you can convert by, okay? So if you have the number of moles, which in a formula, if you looked at this, would be represented by a lowercase n, the number of particles, which is going to be your atoms, that would be represented by an uppercase N, and then the weight in grams, this has it as a W, it's usually just G for grams. So if you're trying to find the weight in grams, and then you're trying to convert that into the number of moles, you would divide that by the molar mass. If you have the number of moles and you're trying to find the mass, you would divide it by its molar mass. And then like so on here. So we will go through some examples and I'll show you. So for the first one, what's the mass in grams of 3.50 moles of the element copper, which is Cu. This would be useful if you are in a lab or you've calculated that you need to use up 3.5 moles of copper, but now you need to figure out like how many grams that's going to be because you need it to be useful for you to measure. We would have to convert it like this. So if you have 3.5 moles of copper, that's what we start with. So we're going to put that in the top left corner of our dimensional analysis boxes. We need to find the mass in grams. So 1 mole would come down here, 1 mole of copper. 1 mole of copper is going to be equal to its atomic mass. So we talked about that here. Whoopsie. Oh, I lost where we talked about it, but that's what it's equal to. So 1 mole of any element is going to be equal to its mass on the periodic table, its average atomic mass. So that's how you do that conversion. So anything. So if this is 1 mole of oxygen, it would be equal to 15.99 grams of oxygen. So once we get this set up, we start with moles. We convert 1 mole into grams. You multiply these, divide it by 1, and then you end up with 222 grams of copper. So if you guys tried this, if you want to try it, you can pause the video here and give it a shot before I explain it. Okay, so what's the mass in grams? 0.375 moles of potassium, which is K. So if we know we have 3.75 moles of potassium, that's going to go in the top left corner. And then moles of potassium would come down and over, just like we would before when we did dimensional analysis. Looking at the periodic table, we know that 1 mole of potassium is equal to 39.1 grams. So we would just do the math and solve this. So we'd end up with 0.375 times 39.1 divided by 1, which gives us 14.7 grams of potassium. Okay. Notice I do have another little triangle down here, so this might be helpful in figuring out how to divide or multiply if you need to. So another example, a chemist produced 11.9 grams of aluminum. How many moles of aluminum were produced? So this would be just the opposite of that. Like you're in a lab and you actually produced 11.9 grams of aluminum. Now you need to convert that back into moles, maybe to do some stoichiometry. So we start with 11.9 grams of aluminum. Grams of aluminum has to come over and down to the bottom. That unit would come over. We know we're converting it into moles, so moles will go on top. But what's different here is we flip this. So we know that 1 mole of anything is going to be equal to its atomic mass off the periodic table. So since we started with grams, grams comes down. So just the only difference here is that you're flipping this conversion. So you're going to have 26.98 grams of aluminum, which you found on the periodic table, is equal to 1 mole. So here's another example if you guys want to pause this and try it yourself first and see if you got it right. So how many moles of calcium, which is Ca, are in 5 grams of calcium? So we know we're starting with 5 grams of calcium, so that'll go in your top left corner. Grams of calcium has to come down and across, and then that we would set that equal to 1 mole because we're finding moles. So for this one, again, you have to find the grams of calcium off the periodic table. So that's its average atomic mass is 40.1 grams. We're going to set that equal to 1 mole. So in this case, you would have 5 times 1. You'd divide that by 40.1. So we end up with 0.125 moles of calcium. For our last example, I believe this is the last one. How many moles of silver are in 3.01 times 10 to the 23rd atoms of silver? So this one won't come up quite as often. You're going to be converting a lot more between moles and mass, but this does come up occasionally. So, and this will be important later on in the year, especially with stoichiometry. So if we start with 3.01 times 10 to the 23rd grams of silver, we know that atoms of silver, my bad. So if you have atoms of silver, that unit has to come down and across. So, excuse me. So if we have atoms of silver, we know that 1 mole of anything is equal to Avogadro's number of atoms. So that's your conversion. So 1 mole of silver is equal to 6.02 times 10 to the 23rd atoms of silver. That's always going to be your conversion. So once we get all of our numbers in the right places, you just solve for this. So it'd be your 3.01 times 10 to the 23rd times 1 divided by 6.02 times 10 to the 23rd. So we end up with 0.5 moles of silver. So if you guys want to pause this again and try this one on your own. So how many moles of lead, which the symbol for lead is Pb, are in 1.50 times 10 to the 12th atoms of lead? So when we start writing this out, we're going to have the value that we're given, which is this many atoms of lead. We know that atoms of lead has to come down to across here. This should say atoms right here, sorry. So we'll pull this unit down here. We know that 1 mole of anything is going to be equal to Avogadro's number. Okay, so it's no different than saying I have a dozen donuts, or I have a dozen frogs, or I have a dozen Tonka trucks. A dozen is a dozen, no matter what you're talking about, right? It doesn't matter if I'm talking about kids in my classroom or dogs I have at home. A dozen means 12. So it's the same with this. So 1 mole is equal to this many atoms, no matter what element you're talking about. So in this case, again, sorry, I got a little sidetracked there, but you have what you started with. You bring atoms down and across. You set that equal to 1 mole because that's what we're trying to get to. And then you just have to solve for that. So you'd have 1.50 times 10 to the 12 times 1 divided by Avogadro's number. So you would end up with 2.5 times 10 to the negative 12 moles of lead. Let's see how many we have left here. Okay, I lied to you. This is the last set. So example problem number 4, this is obviously a little bit longer. You can see that it has more squares in the dimensional analysis boxes. And what the difference is that you are converting like multiple units within this. So we did this a little bit at the beginning of the year when you were converting maybe like how many seconds are in a year. So you'd have multiple boxes. So in this one, what is the mass in grams of 1.2 times 10 to the 8th atoms of copper, which the unit is Cu. So we know we're going to start with our atoms of copper. It's going to be up here. Atoms of copper has to come down and across. So now this is where you need to try to figure out, like, what's my next step going to be? I'm trying to get to mass. We can't go straight from atoms to mass. Okay, we're not going to do that. So you're going to go from atoms to moles and then moles to mass. And unlike dimensional analysis we were doing earlier in the year, this is the pathway you will follow to get to this result. You do not have other like routes to solve that. So you'll want to, and the reason for that, and I know it seems like you could just move the 63.55 over on top, and I guess you could. But later on in the year, this will not just be one single element. This will be a molecule with several different things inside of it, or it could be like a diatomic atom, whatever. It's more simple to leave it the transition from atoms to moles and then moles to grams. I suppose if that works for you and you really want to just squish this over here, you could. But just make sure that you're double checking your answers when you're doing that. Just make sure that you're doing it the right way. So restart here, sorry. Start with what we're given. We have atoms of copper. So atoms of copper comes down here. We know that atoms to moles, 1 mole of anything is equal to Avogadro's number. So we have this many atoms is equal to 1 mole. 1 mole comes down and across. 1 mole is also equal to the atomic mass. So moles kind of like go both ways here. So 1 mole is equal to the atomic mass of whatever element you're talking about. And 1 mole is also equal to 6.02 times 10 to the 23rd atoms. So once we get all of these in the right place, atoms would cancel, moles would cancel. We're left with grams, which is what we are trying to solve. So we would have 1.2 times 10 to the 8th times 1 times 63.55, all divided by 6.02 times 10 to the 23rd times 1, which would give us 1.3 times 10 to the negative 14th grams of copper. So if you guys want to try this very last one on your own, and if you haven't tried any yet, please do pause this right here and try this one on your own just to make sure that you are understanding it as we're going. Okay, so hopefully you paused it and tried it on your own before you went through. So what is the mass in grams of 7.5 times 10 to the 15th atoms of nickel? So you know that you're going to start with 7.5 times 10 to the 15th atoms of nickel. That'll be in your top left corner. Atoms of nickel has to come down and across. We know we can go straight from atoms to moles. I'll just click this so you can see it. So we have atoms of nickel. Atoms of nickel goes here. Atoms, 1 mole of atoms is 6.02 times 10 to the 23rd. That is always true. Okay, so 1 mole of anything is going to be equal to this. So then we're in moles of nickel. Moles of nickel comes down and across. 1 mole of nickel is equal to its average atomic mass, which we found on the periodic table, which is 58.7. So now you solve for this. You will multiply everything across the top. You will multiply everything across the bottom and then divide. So you should have ended up with 7.3 times 10 to the negative 7 grams of nickel. And that is it. That's the end of our slide. Tried to keep that short. I don't feel like it was short. So you guys do have some practice that is on Canvas, obviously. So you'll have some questions like these where you're converting like atoms to moles or moles to grams. And then there's also some average atomic mass questions on the second page. So that's like the beginning of these slides if you need to go back and reference that at all. There's also a video right above this that talks about the radium girls, and there's like a Padlet on the last page of the like where the assignment tab is. So if you would watch that video and respond to the Padlet, that would be great. We're just kind of discussing it in class a little bit, but the reason why I bring up the radium girls is because it talks about, like we were talking about, isotopes. And if you get isotopes that are unstable, they become radioactive. So that's where the radium, or the undark is what it's called. It's this radioactive paint that glows in the dark, and it caused all of these like really severe health issues for these girls in these factories. So if you haven't heard much about the radium girls, it's very, very interesting. The video I posted is pretty short, so I would really recommend watching it, and then just put a little short response there to the Padlet. So if you guys do have any questions, please let me know. I'll be grading the projects this week, potentially over the weekend too, depending on how that goes. Just like you guys, I have other things happening too outside of school. I have family from out of state, and I'm trying to like make time to see them this week a little bit after work. So the grading is going to be just a little bit slower than normal for that because I'm not able to work at home as much this week. So that'll be done by next week for sure. So hang tight on that. But if you do have any questions, let me know. If you guys want to set up a Zoom call or whatever, that's fine. So, yep, that's it. All right. I will talk to you guys next time.